So now that we've introduced the notion of left and right Riemann sums, we're going to go ahead and apply this concept in order to approximate some definite integrals graphically, right? And so here we're asked to use Riemann sums with 4 equal subdivisions to approximate the definite integral from 0 to 2 of negative x squared plus 8 dx. Right, and so here we just said Riemann sums. We didn't really specify whether we want to use left or right Riemann sums. And so what we're going to do is we're going to go ahead and actually try both cases and then kind of see how our results differ. And so here I graphed out f of x equals to negative x squared plus 8. And let's go ahead and actually mark the kind of interval that we care about. So we care about, this would be our upper bound at positive 2. This would be our lower bound right over here at x equals 0. And they're asking us to use 4 equal subdivisions to approximate this integral. And so, each subdivision has to be of equal length, right? And since our length is a total of 2 units, we're going from 0 to 2, right? This entire interval over here has a length of 2 units. Then what we're going to do is we're just going to take this interval and just divide it into 4, right? So 2 divided by 4 is in fact equal to 0.5. And so that gives us the length of each individual subunit, right? And so let's go ahead and, let me just erase that. Let's go ahead and actually mark each individual length, right? So we can draw out these rectangles. And so let me go ahead and do that. So this would be one kind of 0.5 length interval. This is another one, and this is another one. And so now we have we've divided the area beneath the curve into 4 equal length subdivisions, right? We divided this interval into 4 equal subdivisions, and each one has a length of 0.5 because each hash mark represents 0.5 on our graph. And so now what we can do is we can try a left Riemann sum approximation, and then we can try a right Riemann sum approximation. So let's go ahead and actually start with a left Riemann sum approximation and see what happens there. So what we're going to do is we're going to use the value of the function on the left-hand side of each subdivision to create each individual height, or the height for each rectangle, right? So let me just go ahead and draw that out. And we covered this in the previous video, so I hope it's not too foreign to you. And so that will be our final subdivision. Let me draw that a little bit better. So it will look something like that. And so that would be what our Riemann sums would look like if we were to use 4 equal subdivisions. And just looking at it visually, this is just an approximation, right? But we're looking at it visually, we can already tell that this may be an over-approximation because we have some area that's above the curve, right? Some area that is above the curve that we are still including in our Riemann sum. And so we can already tell that this is going to be an over-approximation. But we'll kind of look into that more in a second. So let's just go ahead and actually evaluate now what this Riemann sum would be. So the area over here is going to be equal to the sum of each individual areas, right? And we know that the base length is 0.5. Let's start with this rectangle right over here. 0.5 is our base, and the height is going to be given by the function evaluated at the left-hand side of our kind of partition, right? And so f of 8 is going to be, f of 0 is going to be equal to positive 8. So f of 0, which is in fact positive 8. And then we're going to add that to 0.5 times what is our height for this rectangle right over here. Our height is going to be f of 0.5, and we can go ahead and actually evaluate that. So we know that 0.5 squared is going to be 0.25. So we get negative 0.25 plus 8. That's going to be equal to 7.45. That's going to be 7.75, right? So this is 7.75. And then we can go ahead and add that to 0.5 times, so that's the base length of this rectangle right over here, and the function evaluated at the left-hand side is going to be f of 1. F of 1 in this case is negative 1 plus 8, which is 7, so times 7, plus 0.5 times, again, the base of this rectangle right over here. The height is going to be f of 1.5. So 1.5 squared, I believe that's 9 over 4, which is in fact 2.25. So that's negative 2.25 plus 8, right? And so negative 2.25, let me write this out. 2.25 plus 8, we know that 8 minus 2 is 6. and then minus 0.25, it's going to be 5.75, right? 5.75. We can go ahead and factor out a 0.5. And so we'll get 0.5 times 8 plus 7.75 plus 7 plus 5.75, which is equal to 0.5 times, we know that 8 plus 7 is, what is that, 15. That's going to be 15 plus, and then 7.75 plus 5.75. That 7.75s will form 1.5. 7 plus 5 is 12, so here we'll get 13.5. I hope I'm doing this right, to be honest. 0.5 times, this is going to be, what is that, 28.5, right? 28.5. And we know that this is going to be equal to, this is just 1/2 of 28.5, which is going to be 14.25. And so that would be our area right over there. So that is the area using a left Riemann sum approximation. Let's go ahead and do the same practice, but for a right Riemann sum approximation using, again, 4 equal subdivisions. Let me go ahead and divide this into our interval that we care about right over here. And then let me go ahead and divide this into our 4 equal subdivisions again. But now this time we're going to use a right Riemann sum approximation. So we're going to use the right-hand side of our partition, or the function evaluated at the right-hand side of our partitions, to be the height of each individual rectangle. So let's go ahead and show that. So it's going to look something like this, right? And so here we go. Something like that. And then what we can do now, we can just go ahead and evaluate the individual areas. So over here, this individual area right over here has a length of 0.5, and the height is f of, in this case, it's going to be f of 0.5, right? The function evaluated at 0.5, which, did we do that in the previous portion? F of 0.5 we said was 7.75, right? Plus 0.5 times f of, for this rectangle right over here, base of 0.5, the height is going to be the function evaluated at the right-hand side, so f of 1, which we said was 7, I believe, yep. And then we're going to add that to, again, 0.5 times, for this rectangle, the height is going to be f of 1.5. And then finally, for this rectangle, we have 0.5 times f of 2 as our height. So f of 1.5, let me just remember that was 5.75, right? It's going to be 5.75. And then f of 2 is going to be equal to -4 plus 8, which is, in fact, +4, right? And so then we can go ahead and factor out the 0.5 just to simplify things a little bit. So 7.75 times plus 7 plus 5.75 plus 4, that's going to be equal to 0.5 times 7.75 plus 5.75, again, we said is 13.5 plus 7 plus 4, which is going to be 11. So that's equal to 0.5 times 13.5 plus 11, that is, what, 24.5? Which is going to end up being equal to 14, or not 14, rather 12. Okay, why is this not? 12.25, and so that is our approximate area using a right Riemann sum. And so if we look over here, the left Riemann sum gave us an area of around 14.25, while the right Riemann sum gave us an area of around 12.25. And if we look graphically, we can see that there's still some area over here that's unaccounted for by our right Riemann sums. And if we were to use smaller and smaller subdivisions, then for both of these examples, then these two numbers will get closer and closer to each other, right? They would converge to each other. And so, as the amount of subdivisions we use approaches infinity, then we would end up with the integral. That would be the exact value of this integral right over here. And so we saw that when we used a right Riemann sum, like in this example right down here, we ended up with an under approximation, and we can just tell that graphically. And then if we were to use a left Riemann sum in this case, then we ended up with an over approximation of around 14.25. Again, this is just evident graphically as well. And later on, when we learn how to actually evaluate this integral and get an exact value, then we will come to find that the exact value lies somewhere in between these two numbers right over here. So if we were to actually say something, we could state that 12.25 is less than the integral from 0 to 2 of -x squared plus 8 dx, which is less than 14.25, which is the approximation. So this was our right Riemann sum approximation, and this was our left Riemann sum approximation. And so you should always look, whenever a function is decreasing over your interval, then we know that the left Riemann sum is going to be an overestimate and the right Riemann sum is going to be an underestimate. Meanwhile, if the function is increasing over your interval, as we saw all the way over here, the right Riemann sum is going to be an overestimate while the left Riemann sum is going to be an underestimate. And you can always just think about that intuitively, think about it graphically, draw out an example and kind of just see how you can generalize that, because in general that will be the case, assuming that you aren't using an infinite amount of sums for your equal subdivisions, right? And so when you're using equal subdivisions, that is the general case where the left Riemann sum for an increasing function is going to be an underestimate, while for a decreasing function it will be an overestimate. And if you're using equal subdivisions for a right Riemann sum and the function is increasing, then you'll have an overestimate, and if it's decreasing, then you'll have an underestimate. And this right over here is just one example of how you can use these Riemann sums to approximate these definite integrals graphically.